Good morning. Today's lecture we will continue on registers. So here, last time we stopped at the serial addition register. The advantage of using this register is instead of using we used to make parallel adders in the past, such that each bit has its own full adder. So for example, when we have 4 bits as A3, A2, A1, A0, and we have B3, B2, B1, B0. So in the past we used to say there is sum, carry, sum, carry, sum, carry, sum, and carry. So that was in the past. So we used to make full adder here, full adder here, full adder here, 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 here. So there used to be 4 bits. We need 4 full adders. However, if we can use the benefits of the register and sequential logic circuits, so we can make, instead of inserting the data as parallel, make them as series. So A3, A2, A1, A0. Then we have, will be one input. Let's call it, for example, input X. Then we have B3, B2, B1, B0. There is one input. We can call it Y. Then we can make X and Y with full adders. So we have sum and carry. The carry will go for input Z. Okay? So in order to achieve this, we can use, we need to use shift each bits at once. A0, B0, make sum and carry. Then store the carry bits for the next cycle when we go to A1 and B1. How can we move from A0 to A1, A2, A3? We can use a shift register. So the shift register, basically, we will shift. We can make this, for example, shift right. So after the first cycle, it will be A3, A2, A1, then A0 will be here. And that's what will happen for here, B1. Here's B2, here is B3, then here is B0. So we just shift lefts, or shift right. Then after making this shifts, we can go to the next cycle to make another round of making addition. And so make the sum. But this is can be applied for input and output, X and Y. However, we need also something else which is related to the carry bits. If we keep the carry bit like this, it will be updated automatically. But our target is to hold this carry bits until the next cycle will happen. Therefore, we need to have a memory elements. That memory, which is flip-flop. It can be either D flip-flop, JK flip-flop, T flip-flop. So, for example, here in this example, we will use D flip-flop. So the overall idea, shift register, so we can move between the bits, A0, A1, A2, A3. Then we are using only one full adder. So the advantage of this approach, there is less hardware, less costs, and it's less complicated. While the disadvantage, which is slower. This is slow. Why slow? Because you need to wait, for example, for 4 bits, 4 clock cycles to get the outputs, to get the latest sum. While in the parallel, or when we use this approach, we don't need a clock cycle. Or you can just wait a little bit and it will give you the answer. So the first approach, which is called parallel adders, using this part, it is fast. But it's cost a lot. Cost more logic. We need 4 full adders if we are dealing with 4 bits. How about 5 bits? How about 6 bits? How about 32 bits, 64 bits, 64 adders, full adders? While in serial, we will still use only one full adder. It can be for any number of bits, which means less hardware. So it will cost us the higher number of bits, the more cost that we will save. But the disadvantage, which is slower, because it will take n clock cycles to finish this. So if we have 64 bits, it will take 64 clock cycles to do that. So it depends on your design. So if you want to make it faster, or does it really matters with you to wait 64 bits? Most of the time, yes, it matters. You can wait, that's fine. Sometimes it says, okay, I need to have very fast, so you need to have more hardware. So that's how we implement our designs. If you need more hardware or faster, spend a lot of money, but make it faster or less costs, and I can wait a little bit. Then it depends. Okay? So following this design, how we can make some analysis on this one. So let's say that draw the state table and state diagram for this one. Okay. We have one storage elements, which is this flip-flop. So we have, here is Q, which is based on Z, is the same as Z. This is for present states. Okay? Then what else? We need to have inputs. What are our inputs? X and Y, which comes from A and B. So we have inputs X and Y. Okay, do you agree with me? That's how we make the state table, the generalized state table. Then we have the next states and outputs, right? You agree? Okay, what's the next state? The next state is Q star. And that Q star, which is the same as the carry bits, right? Here's going to be the next state, Q star. The same as the carry bits. So, next state will be the same as the carry bits. How about the outputs? S, right? So, S. Then that's it for the inputs and outputs. Now, how can we make or manipulate this truth table or state table, state diagram? So, state table, we put 0, 0, 0, like the truth table. 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. The same as any truth table. But keep in mind, you need to determine how to select where is the input, where is the output, where is the next states, and so on. Present states and next states. So that's why I like the generalized table. It can be valid. I can use it anywhere. I don't need to say Mealy model or Moore model. Just let's use the generalized table, and that's it. This kind of approach, I don't think it's in the textbook, but I like it because it will make the life much easier. Now, how do we find the next states and the outputs? We know it is adders, so there is sum and carry. So 0 plus 0 plus 0, sum is 0, carry is 0, right? 0 plus 0 plus 1, sum is 1, carry is 0. 0 plus 1 plus 0, sum is 1, carry is 0. 0 plus 1 plus 1, 1 plus 1, 10, which makes it the sum is 0, the carry bit is at 1. 1 plus 0 plus 0, which is going to be 1. So carry is 0, sum is 1. 1 plus 0 plus 1, 10. So carry is 1, sum is 0. 1 plus 1 plus 0, 10, which is carry is 1, sum is 0. 1 plus 1, 10, which is, then there's plus 1, 11. So carry is 1, sum is 1. Then that's it. Okay? Now, how can we draw the state diagram for this? This is the state table. How we can draw the state diagram? How many states do we have? 2. We have 0 and we have 1. That's it. So we can draw 2 circles. I can here is 0 and here is 1. Then here the problem is in the inputs. So we have each one has 4 combination of inputs. So if the input is 0, 0, the output will go to, it will remain at state 0 actually. 0, 0 will remain at state 0 and the output will be 0. Then, this is the first one. The second one, if the inputs is 0, if the input is 0, 1, it will remain at 0 but the output is 1. So, it will remain at 0. So, 0, 1 and the output is 1 here. State 3, if the input is 1, 0, it will remain at 0 and the output is 1. Then we can put another comma. If it is 1, 0, the output is 1. All of them in the same arrow here. Then number 4, if the input is 1, 1, it will go to input 1 and the output is 0. Go to next state 1, 1, 1, and the output is 0. Okay, deal? Then let's go to the next one. If the input is 0, 0, we are at 1. If the input is 0, 0, we will go to state 0 and the output is 1. 0, 0, the output is 1. Then here, if the input is 0, 1, we will remain at 1 and the output is 0. 0, 1, remain at 1, the output is 0. If the input is 1, 0, we will remain at 1 and the output is 0. Then I can write it here. 1, 0, we will remain at 1, the output is 0. Then the last one, if the input is 1, 1, we will remain at 1, but the output will be 1. So I can write it here, 1, 1, and the output will be 1. So that's it. So whenever there are some commas, so we put commas, but keep in mind, don't forget to put the outputs associated with each one. So this is the state table of the adders that's serial addition using this one. Okay? Most likely when we do the state table or we do the state diagram, we don't worry about the serial input, so we don't want to include this into the state table. That's why I include X and Y. Any question? Here, I use D flip-flop. Can I use any other flip-flops? Yes, you can use, actually there's another form by using JK flip-flop. Look at the state table, it should be the same, Q, which is the same as Z, and the other Q, which is the same as C. It will be exactly the same, but we will use JK flip-flop. So in order to make the JK flip-flop, we need to say that we have the next state, we have the present states, we have the next state here. And we need to use JK flip-flop. So JK flip-flop Q star, this is Q star, equals to J Q bar plus K bar Q. Now we need to do something like reverse engineering. So for example here, when the Q is 0, Q star should be 0. So let's substitute 0, J bar 0, which is times 1, plus K bar, which is we yield that J plus K bar equals 0. That for the first one. Now, the second approach, which is when 0, this is 0, 0, 0, 0. Then there is another state when it will be 1, Q star. When it is 1, it will be 1. Let me choose this state because actually it depends on the previous condition sometimes. If the old condition was 0, it will be 0. If the old condition is 1, it will make it 1. So it depends also on the old condition. Therefore, we can say that we can make some assumptions like such that if they are both zeros, because here, yeah, here times 0, I forget this. Okay, let me do it again. I apologize. Let me do it in the first one. When Q star 0 and Q is 0. So here is 0 plus J times 0 bar, which is 1, plus K bar times 0. So this will be removed, then J should be 0. Therefore, we make J 0. Since K bar is removed, then don't care because it's been removed. Okay? Then that's happened for the following states. When we go to the last, or state number 4, Q is 0, Q bar is 1. So here is 1, while J times 1 plus K bar times 0. So this is 0, therefore J will be 1. That's how we get this. Then let's talk about this one. Q star is 0, Q star is 1, Q is 0. So here is 1, then J, okay, so here the present state is 1 and else is 0, yes. 0 times 0 plus K bar times 1. Therefore, we will realize K bar equals 0, then K will equal to 1. That's what we got. And J, since it has been removed, it's don't care. Okay? Then this approach, 1, 1. So 1 equal to J, 1 which is 0, because 1 bar is 0, plus K bar times 1. Therefore, K bar equal to 1, then K equal to 0. That's what we got, and since J has been removed, it will be X. That's it. Okay, do you understand how we figure out? Again, go back to the equation and try to substitute presents, Q star and Q. Then figure out, like, look where is J and K will be. If you find only for J, while there is no reason or there is no way to find K, then K will be don't care, like it has been removed here. Then the same way, if J has been removed, then don't care. Okay? So now, after we put J and K like this way, again, like using D flip-flop was much easy because D, the same as the function that I want to be. But now we have J and K like this way. So what should we do in order to connect JK flip-flop? You need to do K-map for this, K-map for this. So after doing K-map, then you'll figure out what to connect for J, what to connect for K. So I can say, like, let me put them in terms. Here is M0, M1, M2, M3, M4, M5, M6, M7. So let me look at J first. So J is actually M3. Then there is don't care. Don't care. Let me write it like in the right representation. So as min terms, which is we have only 3, while as don't cares we have 4, 5, 6, 7. Then for K, the min terms we have M4. Then for the don't cares we have 0, 1, 2, 3. Now, how can we simplify this in K-maps? So the final format, it should be XY, this one should be X bar, Y bar. How we get this? Let me draw the current K-maps. K-maps for 3 variables. Okay, here is 0, 1, 0, 1, 0, 0, 0, 1, 1, 1, 1, 0, 0, 0, 0, 1, 1, 1, 0. Then here's 0, 1, 2, 3, 4, 5, 6, 7, 0, 1, 2, 3, 4, 5, 6, 7, So here is, because our order is zxy, therefore here will be y, here is will be zx, here is will be y, here is will be zx. Because let's assume as ABC, then we'll put C here and here is AB, right? That's why we put it like this way. Then we will say this is the region of y, this is the region of y, this is the region of z, this is the region of x, here is z, here is x. Now let's look for j, here is j, here is k. In j, we have 1 at 3, then 4, 5, 6, 7, don't care. 4, 5, 6, 7, don't care. In k, we have 1 at 4, then 0, 1, 2, 3, don't care. 0, 1, 2, 3. Now, look at j. Can we combine 8 squares? No. Can we combine 4? 4. I don't think so. So the only way is to combine 2. So we can combine these two. And these two is located between x and y. Okay? Therefore, we got j here equal xy. Then let's look at k. Can we combine 4? No. Combine 2? Yes. How? This side with this side. So this is located in the y bar. Let's look at x bar, y bar. Oh, y. Yeah, it's y bar, x bar. I think here is the location of z. Okay. That's getting confused. Here's z. So here's 0, 1. Okay. Of course, there is no z, then it's going to be x bar, y bar. Okay? And that's what we got here. So, when we draw the circuits, it's the same as, very similar to this one, full adders, but we will keep in mind when we connect j and k, we will connect, for example, j, x, y. Here is x, here is y, so here is x, y. And we will connect k. You can either make it x bar, y bar, or you can make it x plus y, all bars, which is in De Morgan's. And that's what we did here. We used NOR gates, and we use it, here is x, y, so here is x plus y, all bars. And which is the same as x bar plus y, x, y bar, x bar, y times y bar. So it's up to you. You can use it x plus y, all bars, or you can use it x bar, y bar. So you have the choice. But in this design, I don't know why, for some reason, it's been used like we use this one. Okay? Understood? So that's how we make our second design, which is using JK flip-flop, by looking at the design. And if you need to use T flip-flop, it can be in the same way, very similar. You need to, when you build the truth table or this table, you need to pick the like TQ and make sure what the output will be based on the equation. Okay? Do you think you can do it with T flip-flop? Again, with T flip-flop, let me write here in a quick way. I'm going to use a different color. So if you need to use T flip-flop, what's the output will be? So in T flip-flop, Q star equal T exclusive OR with Q. So, which is going to be TQ bar plus T bar Q. If the input 0, 0, so if this 0 equal T plus T bar Q, T bar Q, if the 0 will be plus 0, so this will make it T equals 0, the first one. The second one, it is 0, 0, so it will be 0. Third one, it is 0, 0 will be 0. Here is 0, 1, which means Q is Q star is 1, Q is 0. So it will be 2 plus 0, which will make it 1. Then this one, number 4, we have Q is 1, while Q star is 0. This will make it Q is 1, Q star is 0, so this will make it T bar. Therefore, T will be 1. So it will be another 1s here. Then the last one, when we have 1 and 1, which is we will make it 1 equals to T star, T bar, since they are 1, yeah, you will see only T bar. Therefore, T will be 0, so it will make it 0. Then following the midterms, you will see T equals to the midterms, which is 3, 4, 5, 3, 4, 5, 6. 3, 4, 5, 6. So when we do K-maps, zero, 1, 2, 3, 4, 0, 1, 2, 3, 4, 5, 6, 7. So it will be 1 at 3, 4, 5, 6, 3, 4, 5, 6, 3, 4, 5, 6. Then we can do the simplification, which is, here is Z, here is, no, I think this is Y, here is, let me make sure, here is Z, and here is X. So we can do it like this way, group these two. Group these two, then this one alone. So T will be Z X bar, or X bar Z, plus here is Z Y bar, Y bar, then plus this one X Y Z bar. Then you can draw the circuit for this T flip-flop. Okay? So it's very important to understand this one, or how to make the flip-flops. If you see like any of like in the quizzes or the exams, design serial adders such that using D flip-flop or JK flip-flop or T flip-flop. Now, there is another type of adders called universal, or of registers called universal shift registers. In the previous registers, there was shift lefts or shift rights. So here in the registers, the universal one, it can be as integrated chip as shown here. We can do it either shifts, rights, parallel loads, or no change, hold the data. So on this one, it can cover shift register, it can cover parallel register, it can cover like with parallel loads. So all of the types of the registers that we discussed, it can be all included in one, which is this one. Again, recall the registers that we discussed. Parallel register, then parallel register with load enabled. Then after that, there was that's with load enabled. Sometimes I need to keep the data, sometimes I need to store the data. Then after that, we discuss shift lefts. Then we discuss shift left or rights. Then now the universal register, all of them can be in one. Shift lefts or shift rights, parallel loads, which is the same as the parallel register, or no change, which is to keep the data stored. So this is very unique, and it can be used only in one integrated chip. So as a result, we can say if we are the control units S1 and S0. So you need to locate at the controls, which is we use multiplexers to do all of this control. Multiplexers here. So when S1, S0 are zeros, this means retain the data or store the data, don't change anything, no change. When 0, 1, shift right. The 1 is located at the right, therefore shift right. 1, 0, 1 is located at the left, therefore shift left. So that's how we figure it out. Then 1, 1. Then here, parallel register, which means outputs equal inputs. Okay? So this is the last one of registers that's required in this course. Otherwise, we don't have enough time to cover other stuff. So now let's go to the next topic, which is counters. Counters. So counters can be divided into two parts, which is there is something called ripple counters and there is synchronous counters. Ripple counters are, we can call it asynchronous. What do I mean by synchronous or asynchronous? Synchronous, most likely, something comes with common clock. They are all of the flip-flops sharing the same clock cycle. So we can assume here is flip-flop, here's flip-flop, flip-flop, flip-flop. Then we have a clock here, clock here, clock here, clock here. Then, if they are all sharing same clock, then they will be synchronous. Come on, same clock, and they will be synchronous. Okay? When they are all sharing the same clock. However, we can make 4 flip-flops and they are not sharing the same clock. For example, let's assume this is connected to something, then this one, the clock, the output will be connected to this clock. Then another output connected to this clock, another output connected to this clock. To the clock, not to the flip-flop. Therefore, they have different clocks. So those are called asynchronous. Sometimes ripple. Or something like ripple. In counters, it will be ripple, but this is the asynchronous. Asynchronous, again, each one has its own clock. They are not synchronized. Okay? So, what's the benefits of using each one? In ripple, we can use this as a regular counter. Count 1, 2, 3. You can press this on this one. So you don't need to wait the time clock on this one. So most likely when there is a clock, there will be time. So in asynchronous, we don't need to use this time. While in synchronous counter, there will be the clock cycle exists, but there will be another button to make the counts. So there is either ways. We have something like a push button to make the clock, and this will be the same as the counter, or there will be a clock itself, and there will be a counter alone. So it depends on the design. So which is synchronous and asynchronous. So let's talk about the asynchronous counters, which is the ripple counter. So the ripple counter, as we see here, the clock is connected to counts. Then after that, you will see the output will go to the clock cycle of this one. So therefore, we realize that this is not this kind of counters or this kind of design, this is not synchronous. Again, why? It is not synchronous because each clock is different. They are not sharing the same clock, right? This is the first observation. The second observation, there is a resets, and this is active low, so we can reset the counter. And again, why it's called counter? Why it's not any like? Because it looks like a register. It's 4 bits. The counters is a special case of the registers. So this is, yes, a register, but the difference is we don't have a clock, we have a push buttons called counts. And the registers, we need to use them to store some data, because we have a clock. Each clock cycle we will update the data or retain the data or shift the data. But here we don't have a clock, we have a counts. And who will decide will count? It is you. Or it's the sensor measurement. So we can say how many people are getting inside, and you can count the people. Everyone come inside, you press this button. So you will press this button. It's not the clock tick-tock. It's not like what has been in the registers. Therefore, the counters, again, is a special case of the registers, but this is the purpose of it, which is different than what we use it in the register. So we can create something called ripple counter or synchronous counter. In this one shown in the circuit, it is negative edge because we see a bubble into each triangle. There is a bubble, that's why it's negative edge. Then the outputs here of if each flip-flop is the clock for the next one. That's the points which make its difference. So any update will happen for the next cycle. Then it can be applied for T flip-flop, for D flip-flop, it depends on the design. So how we can achieve this using T flip-flop or D flip-flop? Let's make a study to make a binary counts. So here we are using 4 bits, and we need to make some binary count sequence like 000, 001, 0010, and so on. Sometimes we can connect this to the BCD. We know the BCD system, it is from 0 to 9. So 0000, this is equivalent to 0 in decimal, this is equivalent to 1, equivalent to 2, 3, 4, 5, 6, 7, 8, then we can add 1, 0, 0, 1, 9. So actually, we can make a BCD counter, which is counting, a number can count from 0 to 9, easy, by making this design, which is ripple design or asynchronous counter. How can we do this? How can we achieve this? What you need to do is look at the states. So these are, we can consider this is a state, which is state of 0. The next state will be 1. The next state will be 2, and so on. So when you draw the states diagram, it will look like this. We are at 0, then 1, 2, 3, 4, 5, 6, 7, 8, 9, then back to 0. Okay? That's my design, which is BCD, ripple counter. Start from 0 to 9, and after that, it must reset itself after counting the terminal. It must reset itself. That's what we need. Reset itself. So how can we achieve this? Using different flip-flops. Okay. We can do what we call a state table or state table. After that, we can design our system. So what I prefer, let me make a state table. So we have present states and next states. Present states. Then we have here next states. We will see in the ripple counter, the clock will do the job. When you press clock, it will be 0. Press clock, it will be 1. So you don't need to have an inputs. Because let's make the count go to the clock. So the clock will determine when the next update will happen. So when you press update, press update, press updates. So there is no need to have any inputs. So we have only present state, next states. So present state here, 0, 0, 0, 0. It will go 0, 0, 0, 1. 0, 0, 0, 1 will go to 0, 0, 1, 0. 0, 0, 1, 0 will be 0, 0, 1, 1. 0, 0, 1. 1 will go to 0, 1, 0, 0. 0, 1, 0, 0 will go to 0, 1, 0, 1. 0, 1, 0, 1 will go to 0, 1, 1, 0. 0, 1, 1, 0 will go to 0, 1, 1, 1. I think I still need to have, where can I write this? Okay. I'm sorry, let me, is there a way to copy this? Okay. Let's see. Okay. Now, let's keep going. The counter should end at what's? At 1001. Okay. Then 0111 will go to 1000. 1000 will go to 1001. Then 1001 should go to 0000. Okay? Do you agree with me? Now our target is how to manipulate this. Okay. We can use, since we have 4 bits of, or we have 4 bits, so we need to have 4 elements, which is we have 4 storage elements, which is 4 flip-flops. Then, here is the clock. Here is the clock. Here is the clock. The clock. Come on. So if we are using, let's assume we will use D flip-flop. In using D flip-flop, let's make the clock here connected to the counts. So let's locate, here is the first states. So you will see that, let me call it Q0, here is Q0, Q0 and Q0 star. We will realize that Q0 star equal to Q0 bar, right? So what will happen? Here is Q star. Here is Q bar. This is the star. We will take it the opposite. Take it like this. Take it from the star. Or let me do it in a different way so it can be clearer, easy to follow. So we realized Q bar, Q0 bar, Q0 star, the future, equal Q0 bar, right? You agree with me, right? Therefore, it will be, when you make the connection, here is the bubble, here is without bubble. So we will take the one with the bubble as a feedback. Okay? Then the next one, look at the Q1. Here's Q1 star. So we will realize that Q1 is sometimes 0, sometimes 1, sometimes 0, sometimes 1. So what matters with this, what's make it zeros or make it ones, is when you look at here, here is 0, 1, here is 0, 0. So we can look at if Q1 is 1, it will make it next one 1. Here is 0, 0. Since this is 1, it will make the next state 1. Okay? So we can look at it by mentioning that Q1 star equals to, we'll say 1, 0, 0, 0. It will be when Q1 equal 1, when Q0, it will be equal to Q0. And what else? Here, if it's 1, 1, 0, it will remain 1. Okay, let me look about it here in this one. So Q2 change when Q1 equal 1. Okay, therefore, let me think about it. When Q0 equal 1, so therefore Q star equal Q0. Okay, that's how it's changed its status. Q star equal to Q0. Therefore, in our design, D should go here, or we can do, because this one is asynchronous, so in this one, we can make it, instead of going to the D, we will go make it go to the clock. So the update will happen there. After that, we need to connect in the same way that we did to the bar. Then, the same way the outputs of this one will go to clock, then D will be all in the same sequence connected to negative parts, then D here will to the negative parts, and the output will go to D. That's it. So when we design ripple counter, it will be look like this, because any updates will be depending on the previous one. So in order to move to one here, you need to have both of them once to move to the other one, and so on. So in order to move any other cycle, you need to have all of them like once. Okay? Now, how about the synchronous counter? The synchronous counter, they are all common in clock. So the clock is common here. Therefore, when we have the clock it's common, then there will be a time, like tick-tock. So how can we create the timer since the clock is common? Which is by having another button. It's called count enable. So we will have a clock itself, and we will have a count. So the count will matter here, and the functions that we use in the ripple counter will be different than in the synchronous. So the reason for the enable counts is you would like to make sure to enable what will happen next. Enable what will happen next. But if you didn't enable the counts, which is basically most likely will stay or will remain on, or if you make it 0, it will retain the data. If you make it 1, or you press the button, start counting, or count 1, count 2. So it will be based on your push button. So the difference between synchronous and ripple counter, each flip-flop was connected to the other one. The output of the flip-flop was connected to the clock of the other one. So the counter was connected only at the input of or at the clock of the first flip-flop, like what we see here. The outputs is connected at the clock of the first one. Then after that, everyone will be connected to each flip-flop, corresponding flip-flop. So the output of this one will go to the clock here. The output of this one will go to the clock here. The output of this one will go to the clock here. While this one, they are all sharing the same clock. So what matters, how can I do the count or not? Based on another input, it's called counter or counts enable. So when you press this one, it will make it at 1, 1, 1. The advantage of this one, which is faster than the ripple counter, because when you count, wait for the next clock to go to the other flip-flop, next clock to go to the other flip-flop, so it will take some time. However, this counter, it's synchronous, so when you make it, all of them will work at once. All of the flip-flop will work at once. This is one of the advantage of using the synchronous counter. Okay, let's assume this example. So in order to calculate count from 0 to 2 power n minus 1, when you do this, most likely the number of flip-flops will be 2 power n. What do I mean by this? When you count, the number of flip-flops, n is number of flip-flops, flip-flops. Therefore, the number of numbers that we can count, 2 power n minus 1. Just take this as a rule, as a formula for you. So let's assume n equal 4. Then 2 power 4 minus 1, which is going to be 16 minus 1, then 15. So using 4 bits or 4 flip-flops, we can achieve 0 to 15 counter. Okay? In other words, we can make something called hexadecimal counter. Hexadecimal counter. How can we achieve the hexadecimal counter? Let me draw Q4, Q3, Q2, Q1, each one associated with certain flip-flop. So we have 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1. Okay, come on. I'm gonna shake that a little bit. Then 1, 0, 0, 0, 1, 0, 0, 1, 1, 0, 1, 0, 1, 0, 1, 1, 1, 1, 0, 0, 1, 1, 0, 1, 1, 1, 1, 0, 1, 1, 1, 1. Okay? Now, let's assume we want to use T flip-flop. How can we make our analysis? Recall the equation of T flip-flop, Q of T plus 1 or Q star will be T exclusive OR with Q, or in other words, it's going to be TQ bar plus T bar Q. Okay? Now we need to do for Q1 first. Let's discuss about Q1. Q1, sometimes 0, sometimes 1. Sometimes 0, sometimes 1. Sometimes 0, sometimes 1. So which means if the old status was 0, the next status will be 1. If the old status was 1, the next status will be 0. This means what? This means Q of T plus 1 in Q1. Q1 of T plus 1 equal Q1 bar. Right? Because if it was 0, it will be 1. If it's 1, it will be 0. So if we are designing D flip-flop, then it's easy. We will say D equal Q1 bar, and that's it. But here in this design, it's more difficult, which is we have T flip-flop. How can we deal with this in T flip-flop? We have Q star, Q1 star. Our target is to get this. So how we can achieve it? By saying, comparing, we need 2Q bar plus T bar Q equal Q bar. How can we achieve this? This can happen if and only if T equal 1. Right? Then the first one, done. Let's look at Q2. In Q2, let me make it with different color. Q2, it is 0, 0. Then it will be 1, 1. Then it will be 0, 0, 1, 1, and so on. What's happening? How can we make it 1s? How can we make it 0? So when it is Q2 equal 1, or when Q1 equal 1, the next status will be 0. When it is 0, it will remain as 1. When it is 1, it will be 0. What does this mean? This means it toggles itself when every time when Q1 is 1, it will change itself. Flip it from 0 to 1, or then 1 to 0. So we can say in this one, in Q2, we can say when Q1 equal 1, what will happen? Change status of Q2. So as a result, and also we can say that we need when Q1, it will change its status, we can say Q1, Q2 bar plus Q1 bar, Q2. If that's Q2 of T. That's what's happening. If Q1 is 0, so we can say if Q1 is 0, what will happen? Q2 of T will equal to, which is Q1 is 0, it will be equal to Q2. Then hold. And that's what happens. If Q1 is 1, then Q2 of T will be Q2 bar, which is change. And that's what happened, right? So we realize this is the equation will be. If we are dealing with D flip-flop, we will say this is D. But again, we are talking about T flip-flop, not D flip-flop. So our target is to make equalize, to make Q1, Q2 bar plus Q1 bar, Q2 equals to T2, Q2 bar plus T2 bar, Q2. Then we realize that we can say T2 is equal to Q2. Do you agree with me? So the second one, done. How about the third one? Do we have enough space? Yes, we have some. Third one, which is, let me use another color here, Q3. Let's look at Q3 and see when there will be change. So they are all zeros, and it will change to 1 if both are 1s. Then, no change, no change. When both are 1s, it will change its status. So we can say in Q3, when both Q1 and Q2 equal 1, it will change status. Change status of Q3. Okay? When both are 1s. This means when Q1 and with Q2, or Q1 times Q2. So as a result, we can say Q3 of T equals to Q1, Q2 times Q2 bar plus Q1, Q2 all bar times Q2. Or we can compare it with the first one, like what we did in the first one. We will say that T3 will be Q1, Q2. Okay, it's very similar, but now we have both Q1 and Q2. Understood? I know it's kind of tough. This is the nature of the course, so let's try to live with this. The last one. Is there any other curve left? So, okay. And the last one here, they are all zeros, and it will be changed if and only if all those three are ones. This means if it's Q1, Q2, and Q3 ones. Now it's getting much easier, right? In Q4, when Q1, Q2, and Q3 equal 1, it will change status. Change status of Q3. Therefore, this is a very similar way. We can say T4 will be Q1, Q2, Q3 times this. So therefore, Q4 of T will be Q1, Q2, Q3 times Q4 bar plus Q1, Q2, Q3 bar times Q4. Okay, so what else? How can I achieve this, or how can I draw my design? Now, I already assigned all of these four. Now, I need to make my design. How to make the design? Again, it's 4 based on 4 T flip-flops. So let's draw these 4 flip-flops as shown here. Here is first one, second one. Oh, let me make some spaces. Second, third, fourth. Okay? Now, I'm going to assume all of them positive cycle. There is the design that didn't tell me something else. Here's clock, here's clock, here's clock, here's clock. And keep in mind there must be a clear button. Here is resets, resets, reset. And most likely, as I mentioned earlier, the clear button most likely will be active low. So, here is the clear. So clear, active low. Then the clock. This is the clock cycle. Now, for the design. Here is T, here is Q. Let me say Q0, T0. Or I assume it as 1, actually. Why did I say? Sometimes I say 1. Sometimes I say 2. Okay, Q1, 2, 3, 4. Okay, I didn't use 0. So let me say T1, Q1. T2, Q2. T3, Q3. Q4, Q4. Now look at T. What's the value of T1? It is 1. Then that's it for T1. Connects logic 1. What's the value of T2? Q2. So here is Q1. I'm sorry, what did I say about T? T2, it should be Q1, I apologize. Please fix it, Q1. What's the value of T2? Q1. So Q1 will go direct to T2. What's the value of T3? Q1 times Q2, which is AND. So here is T3. There should be AND gates. We'll go here, which is the AND of Q2 and Q1. That's T3. T4 is the AND of Q1, Q2, and Q3. So there will be AND gates. Here's Q3. Then we need to have a Q2. Here's Q2, and here's Q1. Okay? Then here's Q4. So that's my design. That's the counter that can count hexadecimal from 0 to 5 and reset itself. Okay, any questions? Okay, we are running out of time to go for module N. because we have a quiz. So let's go to the quiz, then later we will continue on this. Thank you.